My name is Peter Cleaver, and the stage is yours.
Well, thanks, Peter. So, good morning, everybody. Thanks for showing up. This is joint work by me, Christian, and my colleague, Germano. We're going to talk about interchip timing synchronization using inexpensive MCUs, and they're right there on the table. Very short intro, very short recap of the problem. The principal problem I explained last year. There's the paper for those who don't have access because you haven't been here last year. We also have stuff on our YouTube channel about it. And then the main topic will be two different approaches for clock synchronization with and without hardware. With hardware gets you better results, but you need the hardware. And yeah, God willing, there'll be a live demo. And we'll also explain a verification method to somehow substantiate our claims about how well stuff can get synchronized. All right, so who are we talking to here? My name's Christian. I am a computer engineer or technische Informatik for the Germans. Studied at the back then Berufsakademie Stuttgart with back then Daimler Chrysler. Got my diploma in 2002 and worked at Bosch for electronic brake systems for a few years. Got my master's from Brunel University in distributed computing systems and spent a lot of time with embedded systems at ITK Engineering, where I became a technical expert. And today I'm doing R&D training and coaching at Cleaver since 2015. And also since that time, I'm a part-time university lecturer, usually on Fridays. And my colleague Germano, of course.
Yeah. I'm Germano Brunacci. I'm an Ingegnere elettronico, so it's electronic engineer from the University of Ferrara in Italy. I graduated in 2000, and I always work like a firmware developer in different companies for different industries, medical, telecommunication, automotive. And since 2010, I've been in the battery business for lithium-ion and also Zebra battery, kind of a special sodium-nickel battery that works at 270 degrees, so very niche product. And then I joined Maserati, and there I was like component responsible for the BMS, battery management system for the Gran Turismo, BEV. And then, since 2023, I joined Cleaver, and I'm in the team with Christian.
So much for us. So let's take a look at the problem. It's a really short recap. I'm going to rush through it. If you want the details, please read last year's paper or watch the video about last year's problem with illustrations and showing clock drift over roughly 2 days in a nice time-lapse recording. Here's the principal problem. We got a distributed system. We have our 3 nodes, A, B, C, and each has their own crystal. And that crystal feeds all of their timers. So here's the timer counter unit, here's the crystal. And here's a field bus that ties them all together. Now, if we have a distributed system, we want to run distributed applications, otherwise we would not have a distributed system. So they fulfill a function by cooperating, like for example, controlling the gates in the facility. So here they are, and the idea is that at the same time of day, all the gates open. So in the morning at 7 a.m., they kind of open, not quite at the same time. And if we look at the local counter values, we can see why. No? That's each node's idea about 7 a.m. And obviously that's not going to fly. So if we put that in the form of a graph, we get something like this. This is the real absolute time that you can measure with that atomic clock in Brunswick with the Physikalisch-Technische Bundesanstalt, and that gives you the real thing over here. None of us have that unless you can receive DCF77, then of course you get it, but only once per second. And that would be the diagonal here, the perfect atomic clock. And here's our nodes A, B, and C. Some are faster, some are slower. First thing we do a coordinate transform, or in human terms, we just declare node A to be our master time reference now. That axis becomes node A's time. We do not need the atomic clock from Brunswick anymore. And That's all we do in the first step. But now we have a reference time inside our system, and that is node A, and everything that follows will be done with that. Now the question is, okay, is it really that bad? What if you are not in the gate business? Then maybe it's not so bad if the stuff doesn't open at the same time. Well, here's a same setup, different application. You collect sensor data on node A every 10 milliseconds or something. You send it to the others for processing. Everything runs. You set up integration test. It's great. And then at 3 a.m. in your lab, this happens. Reception, calculation, reception, calculation. Oh, another calculation, and then the next reception. And then, yeah, same sample used twice. And suddenly everything looks weird. You do a lot of code reviews. You can't find the bug because, yeah, the bug's not in the code. It's this. And of course, it happens at 3 a.m. when nobody's watching. And that leaves our test guys looking like this. Okay, so why does it happen? Because even if this thing runs at 1 megahertz, this runs 20 hertz too slow. This runs 20 hertz too fast. Again, we got the nodes A, B, C, and the colors red, green, and blue. Over time, these are the timer values they will have, and they just keep diverging. So after 7 seconds in this example, there's already a delta of 280 timer ticks between B and C. What do? Principal thing, every now and then, A tells the others the time, just like this. Watch these clocks, I love it. Bing! Germano put that animation in. Sweet. So you do that periodically, and that limits the total amount of error that can accumulate. In our examples, it's 40 here. Now with every 3 seconds, it could creep up to nearly 120, but that's it. No? In the other example, it just keeps growing. Okay, and that's how you look like this. But that was the recap. Now let's talk some solutions. Germano, would you please do the honors?
Yes. So we bring here 2 possible solutions implemented with the Raspberry Pi Pico and Pi Pico 2. So we call them portable and hardware backed. So the portable means that we are using just few hardware resources as possible. Hardware backed, we are doing something better because we exploit some special feature that is inside the microcontroller. Maybe not all the microcontroller has it. Let's see how the thing works in principle. So we have a master node, as we said, and slaves. And then the master creates some synchronization events that, in our case, are the rising edge over a TTL line that runs from the master to the slaves. And then we have a digital communication line. In our case, it is an I2C bus at 100 kilobit per second, so quite slow indeed. And for each pulse, for each synchronization event, the master also sends out the timestamp. The timestamp is the timer value that the master recorded at the time of the rising edge. Each slave has an event, an electrical event, so a rising edge, and then maybe after some time it receives from the I2C the timestamps, so the value of the timer that the master had when he pulses the line. So what the slave do then? So they took the master time and they try to reconstruct the master time within each domain. So you see the lines becomes like the dotted lines, so they kind of match the master time. So we had 2 implementations, as I said. So this is the portable synchronization. How does it work? So we receive an edge from the TTL line, and we tied this edge to an interrupt service routine where we capture the local system timer, which runs at the nominal same frequency as the master, but we saw that there could be some small deviation. So we capture that system timer and we store it in a variable. And then after some time, we receive the timestamp over the I2C, and we also store that value. So it means that for each synchronization events, now we have a couple, we have a pairs of data, and we store this data in a table. And so that's it. When the slave needs to know the master time, we can call a function, we call it calc A from B. So we reconstruct the time as seen into the master at the time B. So when we need it, we can reconstruct the timer of the master. So this is the basic principle of the portable approach. Then we have also the hardware-backed synchronization. This is quite different because here everything goes around a compensated timer. So this is an hardware timer inside the microcontroller, and its frequency is adjusted to match the frequencies of the master timer. So if the compensated timer runs a little bit too faster, we can slow down a little bit so that it will return in sync with the master. So, and how we do it, we have a loop. This time is the compensated timer reading, and we subtract it from the value that we will receive from the I2C. Now we have an error signal, and we feed it into a PID controller, and here basically we have the frequency deviation. So this information here tells us exactly how faster or how slower we are going to compare to the master. That's it. So for instance, let's say that we have 1 ppm deviation, 1 part per million deviation, and we are running a 25 megahertz timer, which is the frequency that we are using. So each tick, 40 nanoseconds. So it means that we need to add or remove 1 tick every 40 milliseconds. So every 1 million ticks, we need to add or remove 1. And this is how it works. So one important thing is that since this is a hardware resource, so we can use it, for instance, to fire the OS scheduler interrupt routine. So now we have a real-time operating system that is scheduled with a timer which matches exactly the same timer of the master. So this is important. Because interesting fact is that we need to insert or skip the tick every now and then, but at very precise location that they are never sub-multiples of the integer. So we need to be accurate, so when to insert or remove the pulse. One simple and fast way is to use the Bresenan line drawing algorithm. So basically on the x-axis, we have so many pulses as we need. Let's say the pulses that we have in 1 second. If we run the Bresenan algorithm every 250 microseconds, for instance, we have 400. It is like we have 4,000 pixels on the x-axis, and then we need to draw a line that has the height corresponding to the frequency deviation. So we run the Bresenan algorithm, and every 250 microseconds, we know if we need to skip 1 pulse or add 1 pulse or go straight and wait for the second for the next time. So this is how it works. And then it's time for the real-time demo.
Let's see, yeah.
What we have here, we have 2 setups. They are almost identical. So each one contains 3 Raspberry Pi and 1 Pi Pico and 1 Pi Pico 2. One is the master, and we have 3 slaves. As I said, there's an I2C communication line and a TTL line connecting all of them. And the one on your left, so is a demo with the portable approach. So the LED is supposed to flash once per second, and the LED is also tied to the bars that you see. We have a digital oscilloscope that captures exactly the moment when the LED are lit on. So when everything is in sync, the bars are perfectly aligned. If something is weird or something, or if there is some error, you see the bars that are slightly moving back and forth. And you can read the x-axis of the oscilloscope is microseconds. So the x scale is basically each division is 100 nanoseconds. And we also have a Python script that runs, you see, time error plot. This is exactly the time error. So when we receive the sync pulse, we have the timer from the master, and we have our own timer before the correction. So when we receive the pulse, we can exactly estimate the error from the local timer to the master time.
This scale here is a microsecond per division, and we can see on the software compensated version that's displayed over here. For the naked eye, yes, they're flashing in sync, and they will stay in sync. But if we take the oscilloscope to the switching edges, we see that, yeah, they're going back like plus minus 1.5 regularly, and sometimes they have outliers that go to plus minus 2, almost 3. Whereas on the nice hardware-backed PID level, what's the division, 100 nano?
Yeah, it's 10 times
So
smaller, yes.
Yeah, 100 nanoseconds per division, and you can see the usual deviation is plus minus 80, 60, 100, and every now and then there's an outlier for 150. So, yep, that's a factor of 10, and it's the same cheap hardware.
On the bottom, on the bottom part, we reported the calculated frequency drift. So we know that the master had 1 million time, the slave 1 million 10, so it means 10 parts per million faster or slower, and this is how it's plotted. The same thing happens with the same vertical scale for the other approach. So this is the error.
The remaining error after correction?
The remaining error after correction. Vertical axes are the same, and this is the clock drift capture from the closed loop. So this is the output of the PID controller.
Yeah, the error signal from the PID controller. Yeah. Yes. So up there is the end result. The management summary is on top, and then on the bottom there is the internals. And they're on the same scale, so yeah, obviously the hardware-backed approach gets you better results. Mm-hmm. Yeah. But what if we disturb them?
Yeah, try.
Yeah, let's do it.
Let's do it.
So let's disturb the slave number 3 on the software compensated one. Now, unfortunately, that's on the extreme right of this ultra-short distance beamer. So
I will do the same on the slave 4. Yeah. So we are disturbing the crystal. So we are touching the crystal with our finger, which is hot. And also we are adding some capacitance to the circuit, so it's not working as intended. So the frequency, you see, is a little bit drifting.
And we're both touching the yellow guy,
yes.
Because that's the
we are touching the same. Maybe Christian is hotter than me, but who knows?
Yeah, I had more coffee.
Yeah, and you see how the frequency, the clock drift is moving, but at the same time the error stays within a certain limit. Yeah. And then we can remove the finger and everything.
And it should cool down again. Well, the capacitance will be gone immediately, but we heated the crystals up a little bit, so they're cooling down. And you can see a short spike on the left where the PID loop needed a moment because of the I component to return, whereas the linear regression software-backed method, in that specific case, can be faster to react to a sudden change. But in long-term stability is usually better with the PID, and you get the added benefit that you have now a corrected time base of which you can base interrupts, like the scheduling for your operating system. And then you get physically distinct boards that all activate their respective tasks, if they have the same task scheme, really at the same time, and they're phase locked and they're no longer going apart. So that's easy to do with FlexRay, but now you can do it with cheap stuff.
So we said that everything is synchronized to the master, so we may try to disturb the master and see what happens.
Let's disturb the master.
So this is, so the master is the red one, but by definition we took it as the truth. So the master will stay on 0, it will not move, but all the others need to catch up with him. And this is how it works.
Yes. And last thing to do is to switch off the compensation at all.
Yes.
So I'll do it on my software-backed approach, and you'll do it on yours. And now you can see how the
the firmware here, they are a little bit different. So on the left side, you see that the error explodes, basically. So in just a few seconds, we are outside the range of the screen. On the right side, I think you have to bring up the picoscope. to see the difference.
That's right. So on the right side, the error is also exploding, but we're unable to recognize it. But if you now look at the switching points, they've just, one runs off to the western horizon, the other goes to the east, and that's it. So we can switch them on again, and sooner or later, they will return to something useful. Okay, we see the LEDs are already switching in a reasonable manner, and Germanos are also returning. And looking back at the graphs. Yeah. Okay, we're back in action. So let's talk about how we determine how good could we get with the approaches. All right, so here's a recording from before. So basically, if you use that capability to do some software event tracing on your chips and you sniff the I2C in hardware, then you get something like this. And basically, the communication that's happening, you can find it again in your traces. So that's the view from inside the device, that's the view from outside. And in fact, we were quite happy how well they match up. This is the good one that Germano built with the PID loop, but it really matches up. So here's the initialization, the first send of the I2C, and it really maps with the start bit. Here's the sync pulse, and it really maps with the sync pulse. Here's the stop bit, and it maps directly to the callback interrupt for the I2C on the first slave, but not on the second, because this was addressed to, well, it matches with both, but this was the address. So this is longer than this one. And then when we send the message to the second slave, this one is longer, and the third slave, this guy. So actually, I'm really happy with that. It works quite well. But how well does it work, and how can we find out? So, in order to tie what's going on in the timer values on the devices to something real, physical, we decided to record timer timestamps and output GPIO pulses. We used 2 separate pins, and we deployed this sequence for our verification signals. The first thing that happens is the GPIO pin designated the outer goes high. Then the next thing that happens is we pull a timer value by starting a stopwatch with our internal timing solution, which basically means read the timer and mark that this is the start of the stopwatch. Then we raise yet another GPIO pin, which we designate to be the inner. Next slide will show why outer inner. Well, this also shows why outer inner, of course. Then we wait for some time, so we get some pulse width to work with. And then we do the reverse operation. We lower the inner pulse. We stop the stopwatch. We lower the outer pulse. So we get a duration for the inner GPIO pulse. We get a duration for the software traced stopwatch. And we get a duration for the outer GPIO pulse. And of course, all of them have an absolute position on a real timeline. But that timeline here comes from the internal timer. That thing shows up on the outside world. And that's the trick. So pulses look like this. We got our outer pulse marked in red. We got our stopwatch in black. And we got our inner pulse marked in blue. For each instance of these packets, we trace this blue thing with our tracing solution T1 in software. And we do these pulses, and we record them with a logic analyzer. And then the whole setup looks like this. So here's the 4 picos right there. Each has a red and a blue line for the outer and inner pulse. These go to the logic analyzers, which are there on the table. And each also reports the timestamps for their black stopwatch over USB to one common repository of timing information here inside T1. The master's time is by definition correct. The others are suspect. If we get the synchronization right, they will match quite closely. If we get it wrong, they will be really bad. Now, how do we find out? By nesting these ones between those and recording all of them on the same logic analyzer from the same clock, which of course is to a certain degree calibrated, but even if it's not, they are all on the same time base on the logic analyzer. That allows us to get a relation between the boards that is real and material, because it's electrical pulses going to the same logic analyzer, and we get a master time. And then we get those things. And that allows us to solve for the error. And because we don't want to do live Gauss elimination here on the talk, that would be a bit boring. Let's explain it graphically. We feed it, of course, in a Python script. And then what you usually see is there's your outer pulse, there's your inner pulse. They always line up quite nice. Of course, we're doing them under interrupt lock. And then the black guy will be offset. So we take the centers, center of the outer pulse, center of the inner. They are usually showing up in the same place. And we're taking the center of the software pulse. And now we have the error here. And that error, the pulse center deviations, would be 0 if the synchronization were perfect, which is it not. And how much it's not, that depends on the number we get. And here's a plot in the same scale for the portable and the hardware-backed solution. So by comparing these center deviations and basically saying, okay, we trace for about 200 milliseconds, we record hundreds of center deviation instances along those, and we just plot them here. And this axis is the deviation. And the whole range, you can't see it from back there, is 5 microseconds. And that's the software solution. And that's the hardware-backed solution. And that's basically the management slide to sell the hardware one, obviously. But there's interesting detail to be seen up here, which Senor Bresenham will show you.
Yeah, we mentioned the Bresenham algorithm. So it's nice to see the Bresenham algorithm at work. So this is the same plot that we see here, but we adjusted the vertical scale, so we expanded it. So now it goes from 0, which is the master, down to, I think, 200 nanoseconds there. And we see the slaves. The interesting part is that you see this slanted edge on the slave, because between the Bresenham intervention, the frequency is not the same as the master, so the pulses are drifting a little bit. And then the Bresenham algorithm kicks in and readjusts the thing. So on average, everything is horizontal. So you see the Bresenham algorithm in action. And the amplitude of the jump is 1 tick. So in this case, 40 nanoseconds. So this is how it works. So you see the more slanted, the more often we need to adjust the clock.
Yeah, and you can see that the point of adjustment happens when we've just crossed the 1 tick threshold.
Yeah.
Okay, now obviously there's some noise in these things, and so let's have Germano take a look at where it might come from.
We see that there are some noise, so they are not perfectly aligned. So where does this noise come from? And so we listed a list of possible sources of error. Maybe there could be also other one. So of course the first one is the quantization noise. So we are using timer with a fixed or with a given frequency. So if we are running at 25 megahertz, for instance, our resolution is 40 nanoseconds. So 40 nanosecond more or 40 nanosecond less is, again, inside 1 tick duration. So this is the minimum that we can, minimum error that we can get. We also are using a logic analyzer that it is running at 62.5 megahertz for this time, this buffer duration. So they add up. And then we also have other errors that are, let's say, inside the microcontroller. So we have latencies between the CPU instruction and the GPIO pin action. So in the Pi Pico, there's a special thing. This is single cycle I/O block. So the latency is by design pretty low. Even though we have 2 different cores. We have two distinct separate SIO blocks, so each core has a direct access to the GPIO pin. So that should be quite fast, but then we have latencies from the CPU and the timer. So the timer is a peripheral, and the core spends some time to get access to the timer value. And so since we are running in the nanosecond, 40 nanoseconds, we are close to the speed of the CPU, I mean the clock of the CPU. So this is also important. And then we have clock jitter. So the oscillators are real oscillators, so they have jitters, of course. And then rounding error. So to have this diagram, we are dealing with very large integer numbers because we are counting at 25 megahertz for hundreds of milliseconds, so we end up with very large number. And in the tool chain, we had to export the data in math and then re-import it, and so maybe there are also some rounding.
And the export in math turned out to be floating point based.
Yeah, so maybe there are also some rounding errors in the tool chain.
Yeah, it was hideous at first. I did some rescaling. Now it's okay-ish, but there is still some room for error in that thing. Yeah. Okay, then back to the conclusion. And the conclusion is basically these are the two approaches, and they have their pros and cons. So the portable one is open loop. It's simpler, and it's an arithmetic-based timestamp. The hardware backed is closed loop, and it needs the hardware to back it. The sync event is detected by an ISR in the simple one and by an ISR with hardware-assisted latency compensation in the hardware-backed. You only need software arithmetic, but that requires the CPU. Here you need to basically feed the Bresenham, but after that you have a hardware timer and the CPU is uninvolved in all the time event generations. So you can fire interrupts, trigger DMAs, all of that stuff. Which means hardware events based on the compensated one are not available here, and they are available here. The requirements are only a GPIO interrupt and a free-running timer, meaning you can do that on an Atmel AVR 8-bit because those two exist there. So that's something to keep in mind. Here we need a GPIO interrupt, a phase adjustment feature on the timer, which the Pi Pico has, and the ability for pulse width measurement for this compensation here. But the CPU load to reconstruct a time is higher here and lower here. Here basically you need just a Bresenham feeder, and here you need to perform linear regression every time you want to compensate a timestamp. And that's pretty much it. So where do we go from here? If you like, to our booth, we're back there, and there's even books, and maybe you can score one or something. So yeah, we'll be happy to take questions, and thank you very much for your attention.
Yeah, thank you very much. Due to the initial delays with the HDMI and USB problems, there's very limited time. Maybe we can take one question if there's one. Otherwise, during the break you can talk to these guys. Is there one question right away? Here we've got one.
Hi. What was the reason to do the inner and outer loops of the GPIO? Didn't really see that.
Yeah, if we only had one GPIO pulse and one timer pulse, we could relate them. But then the question is, for example, is there maybe variability in the latency from the the CPU saying I want a pulse to the I/O pin actually doing something? What if there's the program halts for a moment because of whatnot? No? And with these two pulses that are GPIO based, we basically establish a reference that says, okay, if the assumption holds that the CPU through that SIO block can reliably fire off GPIO pulses with a known timing relationship to each other, and we nest them with the inner and outer, then we can record long sessions with the logic analyzer for seconds and minutes, and we can verify all of them, and if none of them are skewed or anything like that, then at least we are pretty sure that the CPU is running in a predictable and linear fashion under interrupt lock, because there's not something else. Frequency modulated CPU clock, or there's all kinds of dirty stuff that could happen. That's why we did it. But in the end, it turned out, it was good enough that you just take the inner or the outer, the results are the same.
thank you to you guys again. Thank you very much.
Okay.